As you can see, we've nearly come to the end of this section, data representation. We are now on video and we've only got compression to go. So this video really is different to the rest of them. It's more informational for you to sort of look at and understand rather than be answering questions or doing anything on the exam. So I'm going to look at video, which really isn't tested in the exam. It may mention it, but it's certainly not tested. And we're going to look at how video files are created and give an example. Then we're going to recap some of the important concepts from the rest of the unit that we've done. So units, numbers, characters, images and sound. We're going to go back over some of that, and I'm going to add some information that was probably not worth it at the time because it may have extended a video or it may have gone off track a little bit and confused you. But the additional information that I'm going to give you is probably not tested, but again, it's something that you really should know about with computer science. So let's crack on with videos. So what a video is just a sequence of still images called frames. Now, I'm sure that many of you have probably already made videos or edited videos, so that's fine. As long as you understand that there's a picture and it just changes one little bit from one to the next until we finally get a set of images that, when stitched together with a very small amount of time between each one, gives you the impression. It fools the brain into believing that it's moving. Now the problem is with trying to fool the brain is there's a certain speed it needs to move at, otherwise the brain's going to see flicker, or it's going to jerk, or it's just not going to look right. And really the minimum amount to fool the brain is around 20 frames per second. And if you're looking at your TV or something else like that, that's normally in sort of 50 hertz or 60 hertz range. In other words, 50 to 60 frames per second to fool you and stop the flickering. If you take a video camera, a modern video camera, or even your phone, and you record a television program, you may see lines that you can't see with your eyes moving up and down the screen, and that's because you've not got the frame rate synced properly. Obviously, the higher the frame rates, the faster you sort of move, the better the quality of the moving image. The problem is with that, it takes an enormous amount of data, and a lot of that data needs to be stored in memory, not just on the hard drive, but actually physically in the memory. Most computers or cheap laptops these days probably have around about 4 gigs worth of memory, and they're not going to hold a movie. And so actually playing a movie is kind of tricky. And we're going to take a look at that now. We're going to sort of do a calculation on a movie and see what the issue really is. So, for example, if we have a full colour image that's 24-bit or 3-byte colour depth, and we've got an image size of 1024 by 768 pixels, which is roughly the screen size of an old laptop, maybe the white area here as an image size. If we do the calculations and work out what the storage size is for that, it comes to around about 2.4 megabytes per image. Now remember, we've got lots of images to stick together, so 2.4 megabytes is per each image. So if we've got 20 frames a second, we need 20 of them. So 20 times 2.4 gives me 48 megabytes. So for every second of video, I require 48 megabytes. Now, imagine that we want to have a 5-minute video. It's not a very long one, considering that you use Netflix and you download films all the time and watch them. 5 minutes is really short in time, but it's a nice figure to play with. So the 60 seconds in a minute, 5 times 60 seconds gives me a total amount of time of 300 seconds. And we've just worked out that we need 48 megabytes for every second. So if we multiply that by 300 seconds for the length of our video, 48 times 300, we come out with a value of 14,400 megabytes. Or if you do your sort of calculations here by moving it into gigabytes, so divide it by 1,000, you end up with 14.4 gigabytes for a 5-minute video. That is a lot. As I've said, normal laptops are maybe only got 4 gigabytes of memory. That's 3 times the amount of memory that you've got. So we've got a problem with videos. They're really, really large. And the bigger problem is this one. You're into streaming with Netflix and stuff like that, and home broadband speeds are pretty slow. What I want you to notice on this one, because this is quite a trick, says that the average, and this is for the 25th of February 2020, the average home broadband speed is 11 mega, notice this, tiny b, bits per second. It's not 11 megabytes per second, it's 11 megabits per second. So I've got to divide this by 8 to get the true figure in bytes. And basically, if we're sort of at home, a decent speed would be around 50 megabits per second. I know you can probably get 60 or above. Some of you can probably get 100 megabits per second. But notice it is in bits, not bytes. And if you're in school, then a lot of the broadband speed that we use there, it is either 100 megabits, that's what that little cable is going out of the back of your computer into the trunking behind, or maybe we've got a gigabit connection these days, but generally home speeds are around about 50 megabits per second, which is really slow. I seem to be getting lots of things popping up on my computer, so please ignore them. Right, so let's assume that we've got a 50 megabit broadband speed. Now if we divide that by 8 to find out what that is in bytes, it works out to be around about a speed that you can receive information through the internet to your computer around about 6.2 megabytes per second. So every second you can get 6.25 megabytes. Well, we had a 14.4 gigabyte file, which was huge. So let's represent that in, just work the values out. We had 14,400 megabytes. That's what we worked out the image size to be. And if we divide that by the speed that we get, now both of these are in megabytes per second, or in megabytes. So it's going to be okay. We don't need to convert these any further. And if we divide 14,400 by 6.25, we get 2,304 seconds to download that 5-minute video. Now, if you think about that 5-minute video, 5 minutes is 300 seconds, but we need 2,304 to download it. That means it's going to take 38 minutes to stream a 5-minute video. That's just going to be sort of buffering all the time. It's just going to stop, download a bit, stop, download a bit. Wow, it just a 5-minute video with just images. It doesn't even have any sound attached to it. And it's going to take 38 minutes for a 5-minute video. Impossible. So obviously something's going on. Some clever tricks are being used with Netflix and YouTube and everywhere else like that to be able to play videos or stream videos at a decent rate when you've only got a 50 megabits and maybe even slower, maybe down to 11 megabits per second speed. So there's some trickery going on. And really, this is a kind of introduction into our next lesson. I'm going to tell you how that is done in the next lesson. But let's add some sound. Let's see what happens when we add some sound, because the last lesson we looked at creating sound. So let's assume that we record sound for the video and we have a sample rate of 44.1 kilohertz. That is CD quality sound, so that's pretty good. And we're doing a 16-bit sample so that we can pick up some of the quieter noises, but we don't need to have a great sample size, maybe because our speakers aren't good enough, or we just don't need to hear really, really quiet sounds. So judging by this 44.1 and a 16-bit sample, we're going to get a bit rate of 705.6 kilobits per second. Hopefully I've got that right in today's lesson. So remember how to get the bit rate was just to multiply the sample rate by the sample size. We've got the bit rate, and to find out the file size, really we just need to multiply it by the duration. Well, the duration is 5 minutes, which is 300 seconds. So if I multiply those two values together, I get this figure, 211,680 kilobits. Now don't forget we're in bits, so we need to divide by 8 to get the bytes. So if I divide, and I've sort of, instead of using KB, I've multiplied it by 1,000 just to get the bits. So 211,680,000 bits divided by 8 gives me 26,460,000 bytes. Or if we just divide it by a million, we get 26.46 megabytes. Oh, that's not too bad actually, because our total file size before was this size, 14.4 gigabytes, and we're only adding on a very small amount at the end for the sound, 26.46 megabytes. So we end up with 14,426.4 megabytes. So we'll just put the 26 on the end there for the high quality sound. Now, what I've got to say with this high quality sound, and we didn't touch this in the next lesson, in the previous lesson, is that this is just mono sound, one channel, so you get the same sound in both ears. We'd need to multiply this by 2 to actually get stereo sound, and it would increase the file a little bit. We'd probably have 52 megabytes instead of 26, but even so, 52 is not really affecting the overall file size that much. So it's not going to affect the download or the stream if we add sound to the video. Well, that's quite interesting to know. So, okay, that's how we've played around with sort of images and videos and sound, and done a few computations with it all. Hopefully you've understood a little bit about that. Really, I'm going to go now and just recap a little bit about what we've done over the last few weeks. And we started off with bits, nibbles, bytes and so on, and it's okay knowing them or what they are, but we've used them as we've gone through. So in the last slide we were looking at bits and bytes and kilobytes and megabytes. So we used them in our natural language when we were actually talking about things. But it's useful to know what the sizes are, so that's something for you to revise. We've also looked at binary addition and multiplication and division by powers of 2, shifting left and shifting right. Now, that's sort of not in this data representation part of the course, but it was needed to teach you what binary actually does. And I've also missed out the fact that we dealt with logic as well. So we've got all of that information to sort of put together. But the addition, the multiplication and division doesn't really affect the data representation. That's more of a programming task. And I said that we can multiply and divide by powers of 2, so I want to clear this one up, by left shifting and right shifting. We haven't learned how to multiply by 3, for example. So when it's not a power of 2, we've not learned how to multiply a binary number by that. So we've just done what I would call at the moment simple stuff. And some of you may have gone on to do the subtraction with 2's complement, which again is not tested on this course, but it's quite fun to play with. What else have we done? We've converted between binary, denary and hexadecimal. And that's probably been a bit of a challenge and maybe difficult, but why are we doing it? That's the real issue here, is why are we converting between binary, denary and hexadecimal? It's really pointless. However, binary is the computer's natural language, so everything to do with a computer is in binary, whether it's in the outside world, being brought in by a microphone or a guitar or a video camera. It's all got to be in binary for the computer to play with it. If it's sending information out to a printer, it's sending that information out via binary. Even if you're using the internet, everything that comes via the internet is binary. However, we don't speak binary, so normally we want to have numbers. We want to be able to see numbers, and so we kind of like to convert our binary into denary so that we've got some idea of what the number is. However, sometimes numbers aren't good enough. They're not, and I'll show you this in a second, and I'll stop that little bouncing widget at the bottom of my screen, this one here. Hexadecimal numbers are a good way of representing binary numbers. First of all, each hexadecimal digit is only a nibble long, and it only goes from 0 all the way up to F. So you've got A, B, C, D, E and F, along with the normal 0 to 9. But the way that it can be displayed on the screen is quite neat, and it helps us visualize the binary. So let's stop this little bouncing widget down here. There we go. And I'm going to sort of get my virtual machine up again. I'm going to show you that hex editor again. So let's see if I can find it. Here we are. So we had the hex editor. I'm going to start it and I'm going to load up this hello.txt file, because I want to explain one or two things about this. If you are interested in this and if you want to hack, this is the way to do it. And I've put together some videos on hacking, which I will drop in the playlists, but I won't attach them to any videos. You need to go find them. But it does tell you how to hack and how to change programs, maybe get extra lives in your games, things like that. But it's a beginner's guide, so it doesn't go too far. But I'm going to open a file that we've used before. I'm going to open the text file. Where are we? That's on my desktop. It should be hello.txt. There we go. It's only 11 bytes long, so it's rather a small file. Now what I want to talk to you about is what you see here, where the green part is, right the way over to this part, so 0, 0, all the way over to 0F. All of this is the information in the file, and it's displayed in hexadecimal for our purpose. Now we could change the way it's displayed. I want you to look at how neat the hexadecimal values are. They're all in columns, nice and neat. But if I decide to view this in a different way, if I display it as decimal, then you can see that the columns are no longer just 2 digits wide, some are 3, some are 1. It gets a little bit untidy. Not only that, it kind of requires a wider screen. And if I look at a different file, which I shall have a look at in a minute, you'll see that really we don't want to display things in decimal. It just messes our screen up. So the other way of viewing it is in binary. So if I view it in binary, it's all the same. Notice now that, well, it's sort of lined up in order. We've got lots of columns with equal widths, but the information's really, I can't even get to 0F. I'll have to widen it well past the screen. So viewing data as binary, which the computer uses, is not very satisfactory. Viewing it as decimal or denary is more satisfactory. We can understand what these numbers are, but we've got unequal values. We've got 3, 2 or 1 values in our column widths. Not very neat. And if we go back to hexadecimal, then everything gets neat. Everything becomes neat and we can separate things out. On the right hand side here, you can see hello world, which is what this hexadecimal set of values translates into using the ASCII table. This is the representation of the ASCII table. Now, if a value is not in the ASCII table, it doesn't appear in here. Now, we can't really see it very well with hello world, so I'm going to choose another file. Let's see if I can choose. There we go. This is a file, it's just a data file, and as we can see on the right hand side we've got the words. We can read the words, that's nice, but we've also got some dots between all the words. Now if a value, a hexadecimal value such as 22 appears in the ASCII table, it writes out the ASCII character, and that one is a quote mark, and that one is a capital J, and that one is an A. However, if it doesn't, or finds a value which is maybe bigger than 127 in denary, it doesn't know what, well, it doesn't know which table it's using, whether it's ASCII or Unicode, so it just puts a dot in. So here I've got a dot for 0D, the next value along is 0A, and I've just got a dot. It's not distinguishing between the two. So this right hand side is just plucking out from the data all the values in the ASCII table, and that has a nice effect because it tells you that you can read some of the text, okay, and sometimes the text is unreadable, but they're part of the ASCII table. So let's take a look at this file very quickly in binary. So this is nice as ASCII, as hexadecimal, sorry, and if I take a look at this as binary, yeah, I really don't want to be doing that. It's far too much. And again, at the right hand side we've got the ASCII table version of it, but I wouldn't want to be reading that and trying to find different values in there. That's far too hard. And if I display it as decimal or denary, yeah, okay, but can you see here we've got three digits and 2 digits. I'm just looking to see if I've got a single digit in there anywhere. I can't see one, but it's not as neat as the hexadecimal. It's up to you how you look at data, whether you look at it in denary, hexadecimal or binary. It's up to you. Just know that the computer only works on binary, so really that's the only value that we should play around with. As the computer goes, you should either choose denary or hexadecimal. Hexadecimal is probably the better one. Right, so moving on our recap. As binary is the computer's natural language, we've looked at how it represents data such as text, images, sound, and although the computer uses binary, we have used hexadecimal and denary at times to make it clear to us how data is represented. Much easier to read. Text. We've just seen a text file. The computer uses tables such as ASCII or Unicode. In fact, there's a lot of tables. I'm not sure if I can go back and sort of pull up different tables. I'll just give it a second. Not really. But there are so many different versions of tables. Unicode 8, Unicode 16, Unicode 32, Unicode 64, ASCII, EBCDIC, loads of them. And your computer is normally just set to one of them. And the point is that ASCII is probably one of the earliest ones. In fact, it was called ANSI, which only used 7 bits, but now it's been sort of extended to use 8 bits, 1 byte. And each letter in the table has a number associated with it. So, for example, A has the denary value 65. I'm not even going to bother with the hex value at the moment. B is 1 on, which is 66, and C would be 67, and so on. So it's nice and logical how they work through. They're always represented by 1 byte if you're using the ASCII table. And the nice thing about that is that your text files are really easy to calculate. So if it's got 20 characters, it's going to be 20 bytes long. However, if you're dealing with Word, which has, or even PowerPoint, as you can see, which has got words on it, if you inspected those files, they would be completely different. Certainly not the same size as the number of characters used. Unicode is more common these days, because different languages around the world, in fact not all of them have letters, some of them have symbols like Chinese, so we need more bytes to represent those symbols, and Unicode uses either 1, 2 or more bytes to actually represent those characters, the characters around the world. However, the first 127 symbols, no matter which table you use, and there's loads of them, are always the same as the first 127 ASCII table symbols. So really the alphabet is always contained in the first 127 symbols, no matter which table you are using to get your characters from. We also looked back when we were in school on how machine language programs worked, and that's just a table and represented in binary. And we did look briefly at the terms opcode and operand. Now the opcode was the programming instruction, and the operand was what it was operating on, whether it was a memory address or a value. In binary it just looks like this, full 8 bits. It's nice if we separate it out into 2 nibbles so that we can see the operand and the opcode clearly. But the opcode is really gotten from a table. So if I go over here, I've got move, store new accumulator, jump if not 0, and load the accumulator. It's got a binary representation for the program. Now I'm going to jump back over to my little thing here. Now I haven't paid, so I can't access the functionality of this. I'm going to have to use the debug program, but I'm going to take a look at this file here, gym.exe, which is a runnable file. There are 3 kinds of runnable files: bat, com and exe in Windows. Exe stands for execute. It is what we call a program. Everything else is just a data file. So I'm going to start up my command line and go to the right folder. Again, you'll need to know what this does, not how to use it necessarily for your exam. So I'm going to the desktop and I'm going to type debug gym.exe. So that's the program I want to look at, and I just get a line. Now if I type U for unassemble and specify an address, so I'm going to type 100, it's 256 in denary, 100 or 100 is the hexadecimal. If I press enter, it gives me the program. So on the left hand side it's giving me the address in memory of where it is. Then it's giving me some values, and actually this doesn't look like the program, but we can see down here we've got opcodes and we've got operands that go with them. I'm just going to dump 100 so I can see it rather like we did in the hex editor. So we're looking at that kind of display here. So over here I've got the data in memory, or the data on the disk. Over here I've got the ASCII table representation of it. But I'm noticing that although I've got 0, 100 here, the actual page in memory is different. So I'm not looking at the actual start of the program. I can do that by typing U and giving it the full address, 0B7B colon 0100. And if I do that, then this is the actual code for the program. And we can see that here. So let's take a look at these values. I've got FF, FF, 2 FFs, so there they are, the first 2. Then I've got a 55, that's the next value. Then I've got 89E5, 89E5. Then I've got 31CO, 31CO. So really, all of this data here, that's viewed nicely in columns, is pulled out like this. Notice that some are longer, some are shorter. 1 byte, 2 bytes, 4 bytes, depending on the actual instruction. And here are the instructions that make up the program. And this one says push, break pointer, move the stack pointer into the break pointer, and then we've got a little bit of logic. Exclusive OR, 2 registers, the AX and the AX, and then this is a subroutine, and it's telling me to go to 1B, 1E, 0244. So that is maybe the start of the program. So if I go to unassemble 1B, 1E, 0244, that's where it's jumping to, and then I've got some more machine code instructions. I could also take a look at that as a dump. So if I do that, 1B, 1E, 0244, because the program instructions are nice, but I don't know if there are any words or bits of information there for me. There are not. But that is the start of the program. So that's what the opcode was, and its binary equivalent, and we can see the binary equivalent when we were in the hex editor. We can just swap between hex and binary. So this is the opcode here, 001, which is the binary. 0001 is the binary for the opcode STA, and then I've got the nibble 0110, well that's 6, so it stands for store the accumulator at memory address 6. So that was the first term. We played with machine language, and we looked at the little man computer. You probably haven't understood a word of it. That's fine. It's just exposure to it. You'll begin to understand later. So images. So we're getting towards the end here. Images. What I want to point out, and this really pushes us into our next lesson. Here's an image I took. Image 0138.jpg. It's a JPG file. Date taken 8th of May. Excellent. Here's the dimensions of the image. 4,272 pixels wide by 2,848 high. Quite a large picture. And it's giving me the size of 3.2 megabytes. But if I look over this side, and I've marked it out in red, 3.2 megabytes, it's sort of an approximation. It's actually this value, 3,361,447 bytes, but its actual size on the disk is a little bit larger, a little bit small, sorry, 3,358,720 bytes. So there's a kind of discrepancy between the size of the image and what was stored on the disk. But to be honest, you've just taken my word there. If we did the calculation that I showed you, so let's do that one. I've shrunk this one down a little bit. If we did this number, the width times the height, and multiply it by the full colour, which is 3 bytes, we end up with this. 36,499,968 bytes. That's 36 megabytes. However, the computer says I've only used this much bytes. 3 megabytes. Big discrepancy there. There's 10 times. This is 10 times larger than what the computer's reporting. So something is going on in the background, and rather like the video, how we get the video played on your computer when it's so large, and we've got such a large picture here as well, but the computer's got it as a very small one. We're going to deal with that in the next lesson. And if you go back to the start on my list, we're looking at something called compression. So just to finish up now, let's just take a look at colour. I want to just add 1 or 2 things to colour. True colour is the name of the 24-bit representation of colour, or 3 bytes. It looks like this in binary. There are 24 bits there. Count them if you don't believe me. And if I converted that into something a bit more readable called hexadecimal, I've got that nibble there is 1, that nibble there is 6, that nibble there is 1, that nibble there is 6, that nibble there is 1, that nibble there is 6. I've got 1, 6, 1, 6, 1, 6 for my colour. much better to represent it in hexadecimal. But what does this mean? 161616. It's split into three. An amount of red, so the first two are red, the next two are an amount of green, and the last two are an amount of blue. So I've got 16 in red, 16 in green, 16 in blue, kind of mix the palette together, and that gives me a colour. I haven't got a clue what the colour is. Maybe you want to go and find out. We normally call this RGB for red, green and blue. And we call it RGB values. And another set of words that we might use are things like red channel. That's the value for the red amount. The green channel, that's the amount for the green, or the blue channel. So if you're working in Adobe Photoshop or anything else like that, then you might come across this red channel, green channel, blue channel set of words. And it's just an amount of green, an amount of blue, an amount of red. But that is not the whole story, because some images have a transparency. And if we have a transparency, we don't use 24 bits, we use 32 bits or 4 bytes. So it looks like this. You might see this value RGBA standing for red channel, green channel, blue channel, and an alpha channel. Alpha channel is transparency. If it's all 0, I think, so if I've got 0, 0, then you can't see through. If it's FF, that's 255, every bit is filled, then you can, it's just completely transparent. And between those two values, it gives you an amount of transparency. So you can see that depending on how we store our images, it could be 32 bits and not 24. And again, this leads us into our sort of next lesson with the compression. This is one area I could convert RGB. I can compress this RGBA into RGB by losing my alpha channel, and I've compressed my my image. So instead of 4 bytes for every pixel, I'll be using 3 bytes for every pixel. But I'll discuss that more when we do compression. Pretty much finally, and this is what I want you to have a look at for your exercise for today. We've got types of data, and the types of data we can look at are images and sound, moving images, movies, alphanumeric, such as text files, and we didn't really discuss these, but graphics and fonts that are vectors, that's line drawings, cartoons, and fonts which you use in sort of Word. They're all different kinds of data, and they've got their own file types. So for images, we've got, and this is not an exhaustive list, we've got all these. Now I'm going to call all of these bitmaps because that's the kind of file they are. However, this one here, BMP, is actually called bitmap. It's a Windows Paint file, and they just chose the name bitmap to describe it, but they are all bitmapped files. So if you hear an image is a bitmap, or tell me the file type of a bitmapped image, any one of these will do, but only this one here is sort of Windows. It's badly named. So this is JPEG, but sometimes shortened to JPG. I think we saw that earlier on. This one is a GIF. This one is a TIFF, tagged image file format. And this one is a PNG. What I would like you to do in the exercise is research these, give me the names, tell me what they stand for, and explain a little bit about them. There are more, loads more, but these are the basic ones. What I can say is not all of them are viewable in a browser. So for example, BMP is not viewable in a browser. The GIF file is the only one, well, when I say the only one, PNGs are possibly capable of performing animation. So they contain moving images, but they're not movies. But I'll let you find out about those. Sound files, normally they're called WAV files, WAV, or you're probably used to MP3 or AU or AIFF. Again, there's lots of different file types, and it's the next lesson that we're really going to look at the difference between them. Movies, you got the Apple QuickTime Movie, MOV, and then you got MPEG-2, MPEG-4, and probably loads of others. These are normally called codecs, C-O-D-E-C. Again, might be worthwhile looking those up as we go through the next lesson. I am not going to cover every single file type in the next lesson, just give you a flavour of how they're used. Alphanumeric, we've seen that. We've got two file types, ASCII or Unicode, or two standards. This now is not a file type, this is a standard, ASCII and Unicode. And for graphics and fonts, we've got TrueType. They're normally the fonts that you see in Word, and they're scalable. In other words, you can stretch them as much as you like and they do not lose their shape. PDF is also a standard, and that is a very good standard in web pages because it allows you to have a Word document that is viewable on every device. So a Word document is not viewable on an iPhone unless it's got a converter, but a PDF is. This is a PDF file is available on all devices, and PS stands for PostScript, and again that's some sort of printing standard which tells you how to print something out. So we've got lots of different types of data and the standards, and again we'll look at them with compression in the next lesson. Finally, a file structure, which is what I want to point out. We mentioned the word metadata. Whoops. And let's see if I can go back one. There we go. We mentioned the word metadata, which is data about the data. So here's the data, and if we quickly whiz back over to this one, we can see the data here. It's all of these numbers. But there's information at the top of the file about the data. Maybe it's the file size in pixels, the image size in pixels, the width and height. Maybe it's telling you how much colour there is. Maybe it's telling you who the author was. There's a lot of information about the data, and that is called metadata. So that's today's lesson. In the next one, we're going to look at compression, and that will be the end of our data representation topic.